Hello guys, in this video I would like to discuss about emission and absorption spectrum, and also for IPTP higher level I would like to discuss about the energy associated to the electron excitation and returning back to ground state. However, for standard level, the information until this part would actually be sufficient. So first I would like to discuss about wavelength spectrum. So you know that actually waves, so light are waves also, and they have different wavelengths. And what we are going to focus mainly is the visible wavelength, which spans from 400 nanometer to 750 nanometer. So this is actually visible for our eyes. Maybe some of you remember that in your previous levels we did flame test. So flame test, actually we use different metal ions and then we use heat, and then we would see actually that different metal ions produce different colors. And here now in IPTP level we would actually learn the science behind that. So originally electrons are located in what is called their ground state. So this is their initial state. So for example, this is a metal atom. It has one electron here on the outermost orbit, and because of heat, it provides energy, and the electron would be able to get excited. So it gets excited, so it moves to a higher orbit. It moves to a higher energy orbit. How it can move? Because the heat actually provides the energy that is necessary for the electron to move. Well, eventually, because the electron, its original position is in lower orbit, supposed to be here, it cannot really maintain the position in the higher orbit for long. Therefore, this electron will eventually go down and it will release some energy. So it will emit energy associated to a certain wavelength, and we would see it visibly with our eyes as colors. Well, actually depending on the magnitude of going down, it will actually release different wavelengths, but that is more on the higher level. But the idea is that if we provide enough energy, like exact amount of energy for the electrons to go up to a higher orbital level, eventually the electrons will go down, and in the process of going down, because the electron cannot sustain itself for too long, it will release energy that we can perceive. So here we have what is called a continuous spectrum. A continuous spectrum actually means that a light consists of all these colors. So it's not like a single wavelength. So imagine that we have a lamp, and the lamp is actually emitting just one color, let's say red. So means that it only has one color here. So maybe the wavelength is just this part. But for example, like a rainbow, so rainbow, then actually we see many colors there. So it is called a continuous spectrum. Well, here, if we only provide a specific color, it's called discrete spectrum, or like it's a specific wavelength, so one wavelength only. But continuous spectrum actually provides light with multiple wavelengths at once. So for emission spectrum, as we've discussed before, if we provide enough energy for the electrons to go up to a higher level orbit, and then the electron will eventually go down, well, in the process of going down, the electron will emit energy, and then we will perceive these colors. So this is hydrogen emission spectrum. And typically, if a gas is heated, so a gas must be heated, they will exhibit emission spectrum. Because they receive energy, then they are going down. So they will actually produce these specific colors if you have dark background. In this way, actually, we can understand the characteristics of certain gas. So for example, hydrogen, the emission spectrum would always be like this. So we have it here, 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 and here. So if you encounter emission spectrum that is not like this, then we can suspect that that is not hydrogen. So it's very specific. Well, if your gas is actually cooled, or like in a cold gas situation, yeah, more likely that your spectrum that you see will be absorption, so not emission. Meaning that your gas now, instead of actually emitting a certain wavelength, it will absorb wavelength only in this part. But you can see that for a certain element, for example hydrogen, then the wavelength that they are more active usually, yeah, it's here, like specific ones, yeah, either they are heated or cooled, yeah, most likely that these wavelengths will be important. But remember, if you heat a gas, then you will observe emission spectrum, meaning that a color on a dark background, while if you cool a gas, then you will observe absorption spectrum, or missing lines or dark lines on like a, what is it called, continuous spectrum background. So this is actually the science behind. So the electrons going up because of the energy, and then it's going down and emitting energy. For a higher level, then there is an expectation for you to know the exact energy level that is associated to this movement. So let me draw hydrogen. So actually hydrogen was the first atom that is modeled perfectly. They were able to quantify or quantize this energy associated. For example, like it has actually one electron. So hydrogen was the first one to be modeled because it's actually quite simple. It only consists of one electron, meaning that here it's in the first orbit, right? There is no second orbit yet. However, if you produce enough energy, then the hydrogen would be able to move to a second orbit, let's say somewhere here. So it will move, let's say here. Then if you provide enough energy to go to a third orbit, then it will go even to a higher orbit. Yeah, it will go like maybe something like this, then fourth, and so on. So here, let's say this is n equals 1, meaning that this is the first shell, the first orbit, this is the second, this is the third. So given enough energy, the exact amount of energy that is required for the electron to go up to a certain shell, then given enough energy for the electrons to move up to a certain orbit, actually, for example, here, the electron can move up here. So from the first, it can move up to the third. Let's say it can move here. However, once it hits the third, or once it's in a certain position, it does not necessarily mean that it has to go down exactly here. No, it can just go here, or it can go all the way. Okay? So remember, given enough energy, or specifically exact energy, the electron will move to a specific orbit level. Specific. But there is no guarantee that when they go down, since it's not as stable, that they will return to its original energy level or original orbit. So here, let's say that initially your electron is on the first shell, and then it goes to the fourth shell, and then it goes back only to the second orbit. It can do that. It can also go all the way back to the first shell. So here, actually, this is the energy associated with electrons coming back from a certain shell. So any electrons that are coming back to the first shell, to the first, so the closest to the nucleus, it is called Lyman series. It means that wherever you have an electron, and then the electron will return to the first shell, then they will actually produce a UV light. If you want to produce actually a visible light, then your electron must return to the second orbit instead of the first one. So it means that it is called Balmer series. And if you only move back to the third shell, then we have like what is called Paschen series. So this will actually release infrared. And notice here that actually the gap between shells, the widest is actually between the first and the second orbit. So imagine that this is the nucleus, the first shell, maybe like the first shell is something like this, then the second shell is something like this, so the gap is very big. But the The second and the third, actually, it gets tighter and tighter. Tighter and tighter. Yeah, until the sixth, and then so on and so on, until approaching infinity. So if your electron is excited close to infinity, it means that the electron will just go out. Meaning that now we are talking about ionization energy. Because now your electron is gone, so your atom is permanently becoming ion. But that we will talk in another video. But in this case, so your electron gets excited to a certain energy level, it goes down, and when it goes down, it releases a certain amount of energy. Depending on the series, it will release UV light, visible light, or infrared. So let's say that here, just for example, and 1, initially that your electron is in orbital 1, shell 1, and then it goes to shell 3, and then it returns back to shell 2, let's say. Meaning that when it reaches here, and then it goes here, it releases energy. And this energy here actually can be quantified using a formula. Energy equals Planck constant multiplied by the frequency of the photon that is associated with this electron movement. So now let's discuss one example of a probable calculation question. So this often appears. So for example, an electron falls from N3, so means that from third shell to second shell. So it will release a photon with a frequency of 4.57 10 to the power of 14 actually. This supposed to be 14 Hz. Because typically visible, so this is second shell, so it's in Palmer. And it releases visible light, and visible light typically they have between 10 to the power of 14 to 10 to the power of 15 Hz frequency photon. Now we are asked to calculate the energy in electron volt, but of course we have to calculate the energy in joule first. Because according to this formula, if we use the Planck's constant of 6.63 10 negative 34, the unit is in joule second. Therefore, if we multiply everything, then the remaining energy will be in joule. So the energy released will be just 663 10 negative 34 joule second multiplied by this. So 457 10 14 Hertz. Okay, so means that we will have around 3.03 10 negative 19 joule. The thing is that this is still in joule, and in order for joule to be electron volt, then we need to convert. So joule to, if we have electron volt, then you want it to be in joule. You just multiply the electron volt with 1.6 10 negative 19. But if we have electron volt and we want joule, if we have joule and we want electron volt, then we divide. So this you must somehow understand the relationship between these. So meaning that now we have joule and then we want electron volt. So now it means that we have to divide our joule with 1.6 10 negative 19. So we will have 303 19 divided by 1.6 10 negative 19. So it should be around 1.89 electron volt. So the energy associated with the electron volt should be around 1.89 electron volt. So the calculation is actually simple. Most of the time you can also refer to the IP data booklet that they have the most of the data associated there. So what we must know is that, for example, well, let me draw some here. So let's say that this is 1 2 3 4 5. Let's say like this. So let's say that you jump to 4 and then you go back to 2, let's say. So here you need to absorb energy here because you go up. So means that you absorb energy that much. Well, if you go down, so the moment you go down, you will actually emit energy. Yeah, the energy that is emitted, actually will just be this, right? So this is the difference between energy required to go to the fourth compared to energy required to go to the second, to the second, right? So imagine like you see this pink part, so this highlighted part, yeah, it's the yellow part. Wait, let me get a different color. It's the yellow part minus the green part, right? But if you know that the green part is actually energy for the second shell, right? So energy for second shell is like this, while this part is energy for fourth shell. So that is why this is actually electron going from fourth shell to second shell. Most of the time we just see, or we just say that the energy, so the total energy is just energy upper minus energy lower. Yeah, that can be, or it will just be this. Okay, so I hope that this video helps. You at least can expect some calculation question, especially for HL. While for SL standard level, you don't need to expect any calculation question for this part. Thank you guys.